Hello, my name is Shivda, and today we're going to be looking at three problems of inherent unknowability in three different fields, in math, physics, and computer science. And this is really a philosophy topic because I'm going to try and argue that, well, not argue, but just philosophize that there may be some level at which these three kind of inherent unknowability issues are connected. So the first one we're going to look at in computer science is the P equal to NP problem. The second one we're going to look at in physics is the Heisenberg uncertainty principle. Right. And finally, the last one that we look at is h by 2. And the last one we're going to look at is in math, which is Gödel's famous incompleteness theorem. Incompleteness theorems. So you may have heard and know a lot about one or all of these. And they're in some ways really different, but in another respect, they're all about unknowability, some inherent things that we just cannot prove, disprove, or know more about as much as we would like in these three fields. And they're not statements about the current state of technology, or it's not like somebody hasn't been able to come up with a smart solution yet. There really are inherent kind of limitations to our knowledge, and it seems like kind of like some fundamental property of the universe, which almost leads one to think that math, physics, and computer science being so similar in some ways, that these three unknowability issues really be maybe some manifestation of some deeper underlying unknowability. So let's dive into a deep discussion, well, not a deep discussion, but a deeper discussion of each of these and see what exactly each of these entails. There's tons you can read up on this, but we're going to have a superficial discussion, but deeper than just writing them down on the board. Alright, so the first one is the P equal to NP problem in computer science. And before we get into this, let's just look at some definitions. So P represents a set of all problems that are solvable in polynomial time. In other words, something like if I said x to the 5 equal to 32, solve for x. Something which has a polynomial time solution. You could use various methods to do this. Newton's method is an example, where you keep finding it's an iterative method of finding better and better solutions. There are many ways to go about it, but it's a polynomial time algorithm. In other words, the time it takes is some polynomial function of the input size. So say the input size was n, right? And the input size is really the size of the input to the problem. Then the solution, the time to get the solution, is some polynomial function of n, where polynomial is basically axn plus bxn minus 1, blah blah blah. Different powers of n with coefficients summed up, and the highest power coefficient is n. That's what a polynomial of degree n means. NP is the set of problems whose solutions are verifiable in polynomial time. So in other words, solutions are verifiable in polynomial time. So in other words, you may not be able to solve the problem, but if I gave you the solution, if I told you what the answer is, you could verify, there does indeed work, and you could verify that in polynomial time. For example, I may give you a chessboard, a chess position, and you could not find the solution. Just imagine you couldn't find the solution. For you to find the solution, you were not smart enough. It would take exponential time because you're really dumb and you would check every move. You wouldn't be able to reject certain moves as clearly wrong. But if I gave you a solution, right? If I told you play this, play that, you could clearly see that that would be clearly winning, and you would play that. In other words, you could verify the solution very quickly, but you would not be able to come up with it on your own very quickly. And very quickly means in polynomial time. Polynomial, the time it takes is a polynomial function of the input size. That's what NP is. NP complete. These are the hardest NP problems. And what they really are, what they really mean, is that they're problems that if you find a polynomial time solution for them, then all problems in NP would have polynomial time solutions. In other words, all problems in NP can be reduced to them. That's what NP complete problems are. We'll come to them in a minute, an example in a minute. But one last set is NP hard problems. And the difference is that NP hard problems are problems that are at least as hard as any problem in NP. In other words, they can be reduced to a problem in NP, but you know, they may be harder. So let's look at a couple of examples, a couple of quick examples. The subset problem. Given a set of integers, right? 1, 2, minus 34, 68, blah, blah, blah. The question is to find if there is any subset of the set, not including the null set, that sums to 0. In other words, can I pick any combination of these integers, some subset of them, the sum is 0. This is both an NP hard and an NP complete problem. NP hard meaning it's at least as hard as any problem in NP, and NP complete means if you can find a polynomial time algorithm for this, for solving this, then the whole of NP is equal to P. In other words, you can find polynomial time algorithms for any problem in NP. But there are also problems that are NP hard that are not NP complete. For example, the halting problem, which says that given a program and given some input, will the program halt at that input or will it run forever? So this is an example of a problem that's NP hard. In other words, it's at least as hard as any problem in the NP set. But it's not NP complete, meaning if you solve that doesn't mean that everything else will also be solvable in polynomial time. So let's look at a good graph that really explains the relation of these different classes of problems. You have P, which is the set of problems which have polynomial time solutions. Sorry, you have P, right? And then you have NP, of which P is a subset, and this means that set of problems whose solutions are verifiable in polynomial time. Clearly, if you could find a solution in polynomial time, you could also verify the solution in polynomial time, and so P is a subset of NP. And then you have NP complete problems. Which is some subset of NP. In other words, they're the hardest problems in NP. The problems that, if you were to solve them, the whole of NP collapses and would have a polynomial time solution. And then there's the NP hard problems, some of which are NP complete, like integer subset problem, and some of which are not, like the halting problem. So this is a really nice Venn diagram that kind of describes the different classes of problems. The widely held belief by computer scientists all over the world is that P is not equal to NP. Why? Because, I mean, people have been searching for a really, really, really long time to find polynomial time algorithms for solving so many different varieties of NP problems, and nobody has been able to come up with one so far. So, I mean, just based on that, the widely held belief is that P is not equal to NP. It could be, and many people say they will, shave their heads if they found that to be true. But really, this is a widely held belief. In other words, some problems in computer science really seem to be inherently intractable. You don't have polynomial time solutions for them. And exponential solutions are useless because you can never really put those to use. They kind of blow up so quickly. Sure, you can find good approximate solutions, which work very quickly, but really to find an exact closed solution in polynomial time may very well be impossible. This is a kind of an inherent limit of computability. It's not that people aren't smart enough to. It may be, but it's really highly unlikely, and it's some inherent kind of limit to powers of computation. So that's the P equal to NP problem in computer science. Moving on, we're going to look at the Heisenberg uncertainty principle in physics. Which basically says that you cannot tell the position and the momentum of a particle with perfect accuracy at the same time. In other words, the more accurately you tell the position, the less accuracy you have in the momentum or the velocity. Momentum and mass and the velocity. And the more accurately you can tell the momentum, the less accurately you'll be able to tell the position. In other words, one comes at the cost of another. And there's an inherent limit in one's ability to kind of know both of them at the same time. It's often represented as sigma x in sigma p, the variance, standard deviation of position and momentum is greater than or equal to h bar by 2. H bar is Planck's constant. It's nothing but h by 2 pi, where h is Planck's constant, h bar is the reduced Planck's constant, and h is of the order 10 to the negative 34. It's 1 point something, 1.05 something into 10 to the negative 34. Now it's important to note that this is a fundamental property of our physical universe and not something that's created by inefficient technologies. For example, the Heisenberg uncertainty principle is often described as follows. You have an electron, right? And you want to, say, measure its position and momentum. And the idea is that, light, the way we view it is because light from our eye light will reflect off it and reach our eye. But the moment we observe it, right, the fact that light reflected off it and reached our eye will shift it about a little bit. So it's, its velocity and its position change. And so you really can't know it exactly. Well, this is true, but it's not a really good way of describing the problem, because it seems to suggest there's some problem with our method of measuring, which is not true. There's actually an inherent mathematical uncertainty involved, which we'll see in a second. We'll do some simple math to see how that arises. So it's not a problem with our measuring capabilities. It's actually an inherent problem with our universe, with our physical universe. So basically, let the position of a particle, which is described by a wave function in quantum mechanics, psi of xt, is proportional to e to the power I k ikx, or equal to e to the power I px by h bar, where k is the wave function, and it's nothing but the momentum, divided by h bar. So this is a simple independent wave function for single mode with wave function k and momentum p. Now in quantum mechanics, we always deal with probabilities. We can never say anything for sure. The probability that a particle is between point A and B is given by the integral of the wave function squared, absolute value of the wave function squared from A to B. That's the probability of the particle being between A and B. And really, psi of x, the time-independent wave function, is... oh, and I should have said, sorry. So the wave function is a function of position and time. Well, we look at the time-independent wave function, which is, we don't put that time factor in there. The time factor would add a sine or a cosine. And now the wave function is really a combination of different modes, and which can be expressed as proportional to n, a n, e to the I k n x, right? where an represents the contribution of the mode with wave function kn. So each of those kind of different waves has some contribution given by that factor an. And as we pass to the continuous limit and get an equality, we have psi of x equal to 1 by 2 pi h bar. Integral, we integrate from negative infinity to infinity, basically taking into account all possible kn's, right? Instead of summing and having a discrete sum, we integrate to get the values for all possible an's, and an's which are further out will have a smaller combination. Phi of p, where this is phi of p because this is nothing but p by h bar, right? Where p is momentum. By p h. We have that h bar, and we have gp. Now, the idea is here phi of p is called the Fourier transform of psi of x. So whenever you have two quantities like this, right, one which is the Fourier transform of the other, and they show up quite a bit in physics, momentum and position are two examples. Then the basic idea here is that we're adding waves, right? We're looking at those different combinations, and by trying to predict the position more exactly, right, we're adding waves of different momentum. And in other words, the momentum become more ambiguous. We cannot predict it exactly. And this is quantified by calculating the variance, the standard deviation sigma. And similarly, if we measure the momentum more closely, we would find that to be an integral, inverse Fourier transform of the position function, which would again tell us that we know the momentum more closely, but at the cost of mixing wave functions of different positions, and that gives us that inherent uncertainty. So really, this is not being completely rigorous. I mean, I haven't showed you how to calculate the uncertainty. I haven't showed you examples, but this really is an idea, a taste of where the uncertainty principle comes from, and the importance that there's really a mathematical uncertainty, which is a limitation of the universe going on. It's not some problem of means of measurement. And sorry, that should have been 2. And finally, number 3 is Gödel's incompleteness theorem. Two very interesting theorems. The second one really kind of strengthens the first. But the first one says that Gödel calls it a theory. But let's call it a system. And he says that any system or theory T can't be both complete and consistent. Now, what does he mean by that? Basically, let's take a step back. Hilbert, the great mathematician, proposed a series of important mathematical problems which were unresolved at the time. Some of which should be solved since. And his second problem, Hilbert's second problem, was to find a set of axioms that for math that would find a set of complete axioms. That means, given any statement in math, you'd be able to prove that it's true or false from those axioms. He had this idea of formalizing mathematics and making it completely secure on a really strong foundation. Gödel's theorem, unfortunately, showed that that's impossible and gave a big blow to Hilbert's idea by just by the statement. But what does complete and consistent mean exactly? So basically, the way a system works is you have some axioms, some self-evident truths. For example, in geometry, we have a set of 5 axioms. You may have heard some of them, like parallel postulate axiom or Euclid's 5th axiom, or between 2 points there is only one line joining them. Things like that, self-evident truths, which really form the basis of the system, and from those you kind of build everything up. And any theorem, any statement can be proved either true or false from them. That's the idea of a system. Now, Godel says that a system cannot be complete and consistent at the same time. Complete just means that for any statement, right, in the system, you can either prove that the statement is true or false. In other words, you can never say, I don't know, this, or I just can't tell. You can always, with your axioms, say, if you've got enough axioms, you can always say that the given statement you're giving me is true or it's false. Consistent just means that there are no contradictions, meaning that none of the axioms contradict each other, of course, and you can never prove result A to be true and result B to be result A to also to be false using those set of axioms. So that's what consistence is. And Gödel's theorem, which is really kind of unintuitive, counterintuitive, says that no system can be both consistent and complete. In other words, you can't have axioms that lead to non-contradictory results, and I can prove any result to be either true or false. Now, we will kind of go through a sketch of an outline of how he proved this in a bit. By no means in great detail, it'll just be a very, very kind of rough sketch. But let's look for a second at his second incompleteness theorem, which really strengthens the first. This just says that any theory T, or any system that has a statement about its own consistency is inconsistent. In other words, inconsistent, if I tell you that theory T proves that theory T is consistent, that statement is useless. It doesn't give you any information, because inconsistent theories can prove anything, including their own consistency. So Gödel's second theorem of incompleteness really kind of strengthens the first one, and says that, you know, a system proving its own consistency is no big deal. You shouldn't take it seriously. Now let's look at the sketch of the proof for his first theorem. Really, the proof of the second theorem follows in a very, very similar way. What Godel did first is he has numbers called Godel numbers, which basically correspond to statements. So given any statement, right, you can construct a Godel number out of it. And similarly, properties of statements will correspond to properties of those numbers. The second thing he does was to construct a statement, or in other words, construct a Godel number which corresponds to a statement, which basically says that this statement is unprovable. Now this is a simplification of what he's exactly doing, but it's very similar to the sentence, this statement is false. Would you say that sentence that I just said is false or true? Sentence is, this statement is false. Well, if you say it's false, then I'm saying the statement is false, that means it's false, that means it must be true. In one case you have it's true. But if you say it's true, then that means the statement is false is true, that means it's true. In other words, it's true. So that means it's true, but that means it's false, sorry. The statement is false. If that statement is true, then it's false. So there's a contradiction there, and what Godel gets is very similar. The statement is false is kind of an inherent problem with, in this case, the system of English and English grammar and construction. A lot of philosophers have, worked on this problem and talked about it, but it's just really one kind of case of Gödel's idea where, a system can't be complete and consistent at the same time. And a lot of people puzzle their heads about it. And it's not a fault of English, it's a problem of logic and systems in general. And so after he does that, he gets this self-referential statement which says the statement is unprovable, or some version of it. And uses a diagonalization method. The idea comes from Cantor's diagonalization method, where how he proves there are infinitely many numbers. Basically, that and a way to prove that is as follows. Every number has a decimal representation, right? You can represent it in terms of zeros and ones. Or where he proves, the number of numbers is uncountable. So there are different types of infinity. There's countable infinity. In other words, you have countably many things and you have uncountably many things. And the difference is as follows. If they're countably many things, that means you can really put them in a list, right? And it may be infinite, but there is some list that way. You can count them. So let's say that list did exist, right? And let's say this was the list. I'm only showing three elements, but there may be many more. Cantor's diagonalization argument proves that you cannot list them. There always will be one more element by constructing an element which is different from each of those, as follows. From the first sequence, he takes one number. From the second, he takes the second. From the third, he takes the third, and so on, and flips it. If it was 1 here, he makes it 0. If it was 0 here, he makes it 1. If it's 0 here, he makes it 1. The resulting number, and writes each of those in a resulting number. The resulting number will be different to each of those previous numbers in at least one place. So in other words, if you had any list and you said that was the list of everything, sorry buddy, because I could create one more which is really not in that list, which I prove is not in that list. So through a similar argument, Godel basically proves that there's a statement which is neither provable nor disprovable. There's always one more statement you can kind of build, which would neither be provable nor disprovable. If you think you could construct a list of all statements that are, have a clear finite answer. So this is really what Godel's incompleteness theorems are about. And just to wrap up, so we've kind of gone through three inherently unknowability problems in kind of three connected but yet different fields: math, physics, and computer science. And these fields really are related in some sense, but what these unknowability problems really kind of make one feel deep inside through a gut level is that there must be some higher level of uncertainty which is really inherent to our universe, and which kind of propagates its way and shows itself in these different fields. And then really we have different means of describing them. We have a means of describing them through physics, through Heisenberg's uncertainty, through math, through computer science. But really this idea of not us being not clever enough, but something that just can't inherently be done. Like, I couldn't jump 20 feet in the air, but that's my limitation, right? Because my legs aren't strong enough. If I was as good as a flea for its size, I would be able to do that. So it is possible. There's no inherent limitation. Or if I was built, with some stronger material, I would be able to do that. But here we're not talking about 20, 30, a million years down the line. No matter how hard we try, we'll never be able to come up with something solutions to these problems, because it just can't be done. So this idea of impossibility in these three fields, impossibility to problems that one would normally think are very solvable and common sense problems that we could definitely ask, that any logical person could ask. The fact that these problems don't have solutions is kind of mind-boggling and perhaps connected at some higher level as some fundamental unknowability in our universe. I hope you enjoyed it. Thank you.